So let's get started, I guess. Okay. So this is all irrelevant. So let's move that out of view. Okay. Okay. Right now, I only have some boilerplate code that I wrote as a means for today. It took me a few hours, so that would have taken the entire stream for today. So just to get some things out of the way, and we're going to move on to compression. So what is compression? Compression is basically saying the same thing in fewer words. So, like, if I write 1 and like 12 zeros like this, that's 9, 12, I think. That's a pretty large number. You could write 1 and 12 zeros. And that is slightly shorter. Actually, so I could add more zeros, like 15, 18, 21, 24. And we could just write 24 zeros. And that's much shorter, and we can go forever. Oops. Let's put that in comments. Okay. And yeah, so there are plenty of things that take a few words to say, but that can be expanded into a very big definition. A good example of this is an image or a video. So if you're looking, so I think it's, well, you don't see my hand very well, but it's here on the right of the screen. You see you see a lot of black points. So in your computer, at some point, to be able to print that on screen, is just like there's a ton of bits that are turned to 0, because 0 is the number of black. So you have black, 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 black. This pixel is black, and that pixel is black, and every single of these pixels are black. Because at the end of the day, you're just turning on and off some lights on your screen. So you need to represent somehow each individual pixel. But a way shorter way to describe this picture is to say, like, from pixel somewhere over here, a bit over my finger here, up to down here, and all the way to the right is all black pixels. That is much shorter. I also want to get something out of the way. When you're compressing image or video, there are a number of so-called lossy compression schemes, which don't say quite the same thing in fewer words, but like something similar. And sometimes you see glitches or very big pixels, like big squares of a single color, where they should be much more in JPEG, for instance. And that's called lossy compression, and that is not the subject of today. Today, we're going to be concerned with saying the same thing with fewer words, and we are going to be concerned with a generic way to do this. So we're not interested in like knowing the domain specific thing. It's a generic algorithm, and it operates on lists of symbols or strings of symbols. So it just knows a sequence of symbols, a finite sequence of symbols, and it's going to make a better sequence of symbols. Or maybe better. It's going to make a smaller one that is better for storage or for transmission. One of the reasons why we compress video is that this way I can send you video in real time. But when it comes to printing video, then having it uncompressed, displaying video, having it uncompressed is really the right solution. So we're going to do that in Haskell because it's very adapted for this sort of presentations. It's not going to be very fancy Haskell. The only piece of fanciness that I'm going to use is I'm going to use the type ISO prime or ISO from the lens library because it represents bidirectional transformations. And of course, when you compress something, you need to decompress it as well. Right. And I need to remember what is the way to reverse an ISO, but we'll do that in a minute. I always forget standard libraries. People who know me know that I do. We're going to start by defining a few examples. Like we can define nines, and it says, so we're going to consider like sequence of digits from 0 to 9. And I made a type for this, which is fin10. And hope it's going to work. And yeah, most of those things I did to prepare for that are untested. So expect glitches in this video. It's very much a learning video, so I don't want to like throw a lot of knowledge very fast. I want it to develop as it goes. So mistakes are part of the fun. So nines, let's say it's repeat 100 times 9. Does that work? Why is it integer? Okay, let me check. Is Dante on? I didn't turn Dante on, so let's turn Dante on. And what is Dante type at? It's point. Okay. That is starting well. Okay, what is the type of repeat then? A bit bigger. It looks readable. Oh, it was replicate. Okay. So just as a validation, we're going to show nines. That is weird. Okay, so that's a lot of nines. So it's a pretty long list. It lasts for a while. What is okay? So if I just run like this, they can run for a while. And here, my definition of nines is very simple. It's very short. So we have a way shorter way to say the same thing here. Similarly, we can make another example, which we'll call cycles. It's also a list of fin10. And cycles is, which one is it? It's not repeat, it's cycle of 0 to 9. Okay, I didn't define enum, so I need to, okay. I didn't know that I needed to do that. That's a bit annoying, but here we go. Fantastic. And again, we are going to show cycles. Oh, shoot. I shouldn't have done that. I need to kill whatever's working. Because I think it's going to loop forever. I forgot something. I don't know where Haskell is running, but I don't know what's happening. It doesn't seem to be doing too much damage for the moment. With a bit of luck, we won't have a problem. So I want to take like 100 of these. And now I can true cycles. But I may have to... What happens if I kill this? Ooh, and my Emacs just froze. Okay. Let me run another Emacs. And we're going to replace that one, this one by that one. Chip. So, which one is it? That looks like that one. Yeah. Okay. And light theme. We're going back to source, lib.hs, to the bottom. And we have the correct definition of cycles. And, oh, I need to run Dante. Here we go. So here we just say 0, 1, 2, 3, 4, 5, 6, 7, 9, 0, 1, 2, 3, 4, 5, 6, 7, 9. Again, a fairly short definition and a very big string. This one is a bit long, actually. Let's make it shorter because 1,000 characters. We're going to implement very inefficient. Oh, no, sorry, that was the right one. I didn't cycle the 100th time. I am totally prepared. So here we go. We have examples. And in a way, what we want to do is to find an algorithm that will find something that is a bit like this, like the short one-line description of these things. Of course, it cannot really do this because it has to be generic. We shoot a bunch of Emacs-related things. Oops. DACID again. Okay. So we cannot quite get that because it needs a lot of domain knowledge to do this. And in fact, the best compression algorithm will sometimes be stumped and will there will be some things which have very short description, and the compression algorithm won't be able to check this. No, not to check it, to find it. It will still give something very long. So compression algorithm, they work backwards. They just say, oh, what similarities do I see? What things do I see that I can exploit to make a shorter description? And and there's basically two things we can think about immediately. These two things are, if a number happens much more than another, or a symbol happens much more than another, then we can sort of try to give it to code it with less symbols. So we don't have to weigh the symbol the same. At the end of the day, we're going to turn everything into bits. So if I have a symbol that I use almost everywhere, I can say, okay, I'm going to use one single bit to represent that number, and I'm going to use more bits for the other ones that appear much less often. This, by the way, is related to entropy in information theory, if you want to look that up at some point. I'll put links to the Wikipedia page. And the idea of finding a small representation, a small set of instruction to represent data is related to Kolmogorov Kolmogorov complexity, I think it's usually called, after a Russian mathematician, Kolmogorov, which I don't remember the first name of. Okay, so finding trying to do this, giving less bits to numbers that happen a lot, or letters or symbols that happen a lot, is called entropy encoding. And it's a bit harder, so we're going to do it last. But there's something else that we can do immediately, is take advantage of the fact that sometimes we have a bunch of things in a sequence. And this is called run length encoding. So we're going to define it. Run length encoding. Okay, so I'm tapping. Yeah, here we go. And this will be an ISO from a list of an ISO prime from a list of A to a list of A and int. So each integer, sorry. So we're going to say, instead of saying, oh, there's an A, we're going to say, oh, there's an A, then there's an A. We're going to say, oh, there are 3 A's. That's fairly easy to write. So we're going to get right to it. Encoding. I can't type tonight. Equal ISO encode decode. Where encodes equal decode equals underscore. Okay. There's an H missing. Wow. It's not supposed to take any time to do this. So to encode the list, we are going to do so we have a list L, and we're going to do group L. That gives us a list of lists. Then we're going to replace each list map okay, I can't. Okay, where is it? Okay, lambda A ace. So a list of A is replaced by all of non-zero length. So we can also first A and length of A's. First A's. Yeah. Yeah, what's happening? Yeah, no. Okay, something I mistyped it. Okay, never mind. Group. I'm a tad confused. Couldn't match type A1 with A2, A0. Oh, that's because I said first instead of saying head. Fantastic. Oops. I need eq. Good. And to decode a list is about as easy. We map. We concat map actually. We concat map a function that takes, so we get a pair of A and of its length, n, let's say. And we return replicate and A and L. So we're done. We are going now to it's a bit abstract, but we're going to write an example. So we're going to do display input dot. So I need to check something in lens. Which is how do I reverse an ISO? I always forget. Well, I forget everything, so that's not. Are you under mapping simple non-anon curried flipped? No, that's not it. Reversing involuted. That's annoying. Was it from? Oh, that's from. Okay. So from this display output run length encoding. That's oops. That's our first example. I'm guessing, yeah, the type variables are a bit hard. So x1 takes something of type eq and returns, well, it has exactly the same type as this, so let's just copy it. Maybe I'll need something more. Okay. So now I can do x1 at so view okay x1 at fin10 of nines. Patterns. Did you mean to use type application? I'm supposed to have type application. Okay, interesting. So because we have types, we can avoid this. I'm surprised. Ah. Oh, that's on me. Okay, well that gives me, oh, there's 100 lines in a row. And that's pretty compressed. Remember, this was what I started with. And what I got is about as compressed as this. I think it's even more compressed in a way, but there's the entire, the code program that is encoded in this as well. Also, display was supposed to use debug trace. Oh, maybe that doesn't work. GHCI. Let's have a look. What? Oh, I can't paste. Okay. Okay. That's a bit annoying. I don't know why this doesn't work. I was supposed to be able to show you some information. Like if I view display, display test. Maybe I should have tested. Let me copy this. Okay. So what are my arguments? Sorry. I need a type of display. Okay. And now I just wanted to describe, not view. Nines. Okay, so that doesn't show. Did something wrong. Or maybe it doesn't work in the HCI, but that would be terrible. Trace. Okay, that's surprising. Set unit. Oh, I see. I see what I did wrong. I just used the wrong type for trace. If you type it works indeed. So it's just that I need to remove this. Okay, so that was a bit embarrassing, but you know. So let's see how it goes. Okay, so it didn't display the output. Does it start? Oh yeah, that's because what I want to do is not view, it's just round trip. We take some ISO prime A B and return an A to A and round trip of F and A is view from A dot view A dot, well, I don't need to, well, okay. View F. So that's an F. And I don't need that particular thing. Okay. We're back on track. And now I do round trip. This will all become meaningful soon. Okay. So, right. And we also need to display the encoded version, a compressed. What's wrong with this? Oh, that's just because I'm lacking an instance of sizable. Instance sizable A. The sizable means there's a size for storage, basically. I just made it up. Sizable AB, where instance, size of AB equals size of A plus size of B. Oops. And now it works. And now we can start doing this again. Here we go. So this is what we wanted to do. Isn't that fantastic? We managed to compress a stream. And it says, okay, I moved from something of size 333. So it's counting, like, I don't know, 3.33 bits. This is in bits. It's going to take 3.33 bits per number, and it's been moved to something of size 10. And we see that we could decode it again to the right thing. Fantastic. Okay, so that's our first step. Half an hour in, but 20 minutes in, I guess. So, but anyway, that's our first step. And there's a bit of a problem with this, is that this is an integer of arbitrary size, which doesn't have a finite number of symbols to represent it. And our algorithms tend to work on finite numbers of symbols. So there are basically two choices here that can be used. Both of them are used in actual algorithms. But so these two things are either I say, okay, I take runs of a maximal length. So say maybe 255 or 256. That's my maximum length. If it's longer than this, then I don't care, and I'll cut the run, and I start a second run. So that's one way, and you would end up with 256 symbols. Maybe 32 symbols would be better. So you just take length of size 32. They don't happen that often anyway, so that's fine. Or you get to encode the number with a finite number of symbols, which is what we're going to do eventually. But we're going to take a bit of a long way to there. So keep that in mind. We have two things on the stack that we are interested in encoding frequencies. So if a symbol is more frequent than others, we want to give it less bits, and that we will be encoding the length of runs like this with symbols. But first, let's consider our other example. So cycles. Oh, that's bad. This doesn't compress at all. In fact, the compressed air quote version is bigger according to my size counter. It isn't actually bigger, but still a bit. So let's do something too. Let's say just to remove some boilerplate. We do view. That's $1. That's an A, and all this is seek unit. So really we're not doing anything except it doesn't have the right type. Oops. Okay. And now if we do this, we're going to remove one line. Yeah. Okay. So it's really an avatar because all of these are ones here. And so we can remove all these ones and get back to the initial encoding of 333. But we have gained nothing. So the natural question becomes, is there a way, because there's a lot of repetition here, and is there a way to transform these repetitions into runs? And if you think about it, there is definitely one way. It's called sort. If I sort cycles, I run this, then I get 10 zeros, then 10 ones, then 10 like that. It's all right. Should make sure that I always have a line at the bottom. Anyway, what is this? Okay, so zeros and ones and twos and threes. Of course, if I do a bunch, like if I take that again, if I take this and I also do a round trip of x1, I should call it algo1. Let's call it algo1. And yep, something will go right. I'll check x1 with algo1. Okay, so if I run algo1 on this, and run trip of algo1 on this, sorry. What I do wrong? Nothing wrong, I think. Okay. Now suddenly the compressed size is impressive. It's like 67. It says, oh, I've got 10 zeros and 10 ones and 10 twos. That's very, very, very good. Except I've got a problem. There is no way to come from this and get back to the cycle without additional information. Zero, none whatsoever. Ouch. Well, I say ouch, but you know what's coming. What's coming is first T. But when T has come, I've served it. Thank you, me. I guess it's thank me then. So the idea now is to find an algorithm that will, well, it won't be as good as sorting eventually, but they would do part of the job, and that I can decode. And this algorithm is called, what is it called? Let me not mispronounce it. It's the Burrows-Wheeler transform. Oh, I didn't mention it yet, but the algorithm we're implementing is based on the bzip2 algorithm. That's probably implemented in your computer somewhere. Because it's the most interesting in my opinion. That's all. So Burrows-Wheeler transform is our next step. So how does the Burrows-Wheeler transform work? We start. There's a good example with banana here. We start with a word. We need an extra character for the last one, which I'll provide in a second. We'll have to implement a ton of instances for it, but let's do this. So we need an extra character for the decoding. Anyway, we take the word banana. You can ignore the small hat, and we take all the cycles of it. So now it starts with the last character, and then like it starts with the A, and like it starts with the N. It's all cycles. You take the last letter and you put it first, and you do that repeatedly, and you take all of these, and then you sort them in alphabetical order. All of these lines in alphabetical order, and you take the last column. So why does that even work? Well, the authors take the examples of the word "the" in English. If you have a text in English and you have a lot of occurrence of the word "the," then all the he, the HE will be together because this thing is sorted. The first column is sorted, but the column before contains the letters just before the he. So in particular, it will contain all the t's, and often they will be together. Not only together, they might be with something else. There might be capital T's, and there might be like I don't know, C's and H's, but there will be a lot of T's. And so you will suddenly have a lot of runs appearing. But the interesting thing about this is that you can revert it, because if you know the last column, then you also know the first one. It's just the sort of all the symbols. And if you know the last column and the first column, then you can put these first column as the last one. You sort it again, and suddenly the second column appears, etc., because of all these cyclical implementations, thingies, stuff. So it's very easy to do, except I've never done it. So we're going to try. So first, I'm going to give myself an extra type. With end, like with end of string, equal, symbol. I forgot. I need an A. Okay, symbol of A or EOS. Yeah, I can't find things on my keyboards. Okay, I will speak one day. I will be able to enunciate. Okay, so that's our thing. We need to be finite and we need to be sizable for the rest. So let's implement things like right away. So instance finite of A implies. So if I have a finite type, then adding one character is also a finite type. That should be fairly obvious. So I define finite as having a list of elements equals elements at A plus map sim elements at A plus we just put the end of stream at the end. I don't think it changes much. It is not. Okay. I'm looking for class finite. It is. Oh, I forgot to write finite. Okay. And I think I will need to prove ORD, but that's fairly. That can be derived. Okay. I cannot deduce ORD, but we can do this. Deriving ORD. I'll help with the parentheses, even if it's not really needed. Oh, now I need it. Okay. So these are good and sizable. A. So we're going to be pretty sizable. We're going to be pessimistic, but and we're just going to add a bit, a full bit, size of x equal size of sim okay, we're going to do something like x equals 1 plus spaces size of x and we're just going to use 1 bit for the last symbol. That is fairly pessimistic, but good one. Yep. I'm typing random things on my keyboard. I hope you enjoy this. Okay, so now we can start working on our Buller's-Willow transform. I'm going to do BWT because otherwise way too long. It takes it's an isoprime again. It takes any list of symbols and it returns a list with EOS symbols of the same symbols. Probably will need more properties later. Evidently will need them. So again, same ISO, encode, decode, where encode equal decode equal. Oh, I forgot to do something. I hope you're enjoying my typing very slowly. Let me take just. Okay. Okay. Oh my god. I'm constantly typing in the wrong place. Okay, so we're going to do something. We're going to do a function cyclic rotations. It takes a list, assume finite, and returns a list of lists. We're going to look at it in a minute. List of list of n. Yes. Cyclic rotations equal. So it will be right plus plus left. We're going to take n. We need some need initial lists, so a's. So n is any number between 0 and length of a is -1. And what we're going to do with this is we're going to say left right is split at, I think, yeah, split at n a's. I think it's supposed to be a colon. Comma, sorry. Okay, what's the problem here? Oh. Can I do let? I think I can do let. Let equal. Yay. So what does that do? It just gives me all the cyclic rotations. We're going to test it with bananas. Banana. So if I write cyclic rotations of banana. So if you wonder, strings are lists in Haskell. This is weird. And now we have all the cyclic rotations. It's not very clear with banana. Let's try again with Mississippi. So here. No, that was well, okay. That's clearly. I should have taken a better word, like Arno. Very narcissistic of me. Now we can see the letters are right in order. They're just cyclically rotated. Okay. So now that we have this, we can uncomment this if I manage to press the right button. First try now with EOS. Yeah, because that's this shouldn't be capitalized. Okay, so now we want to encode, a list of symbol, call them A's. So we need all the cyclic rotations of A's, rotations of A's, and we're going to do something for them with them. What we're going to do is we're going to transpose them. So transforming a list into column. Okay, I'm just going to demonstrate something. Transpose. Actually, I forgot to do something before transpose, but yeah, I think that's just the oops. I'm pressing the wrong button again. Okay. So do this. Okay. So now it's just well, it has all the letters again, but it's the same. What? Why is that the same? Okay, let's do a bit of sort in between. Yeah, let's just run the thing. So let's sort this. If I sort them, then I get all the A's and then the D's and then the N and the R and the D. And if I transpose the sort of it, right. So now I got something, and this is the one that has two A's. Well, it's not the only one, but this one has two A's in a row. They all have them, actually. And this is enough to recover the other ones. So we can do the same thing with the Mississippi River. Let's have a bit of fun. Okay, let's run this. Right. So see how it sort of brings things together. So if I look at the last one, which is the one I'm going to select, it has 3 E's, 2 S's here, etc. It is pretty cool. So again, that is sort, transport, transpose, and last. It is a very inefficient implementation of this. Another remarkable things about the Burrows-Wheeler transform, the Burrows-Wheeler transform, sorry to butcher these names, is that there's actually a fast implementation of it, which I don't know. So to decode this, what's the best implementation of that? So I forgot to add. It is not true. It's I need to add something here. It doesn't have the right type otherwise. Oh yeah, it didn't complain because it's commented out. I forgot to uncomment it. Okay. Welcome to my stream where things happen. Yeah. So I need to add simp on top of all of these, and I also need to add EOS at the end. And it says, oh, I need something to be ordered. So let's just do this. Okay. So to decode my word, I am going to. It's a bit more complicated. So our goal will be to do n times something. So how do I want to present this? Well, we're going to do a decode loop, and we'll see what we need. So we need the word that we're decoding. We need our state, and we need n. And if n equals 0, then we're going to do something to exit. Yeah, extract, let's say, the state. Else, we're going to, let's put that in the second line. And we're defining extract after. Is compression like fractaling patterns in the data and annexing it? What do you mean by annexing? Hello, by the way, Coco Pickle, and welcome to the stream. Yeah, it's basically about finding patterns, or trying to, but it's finding patterns in a generic invertible way. So extracts equal. Okay. And that will not be well typed. Well formed. It's equal in Haskell. So what we're doing right now, Coco Pickle, is we've already found a way to yeah, it's pretty much it. So if you took at the first algorithm we've implemented was take a bunch of things that have that are the same in a row, and just represent them as it's that thing that many times. But that only works if you have things like this. And here we have an example of something that has 10 zeros, 10 ones, etc. And we can find that. And what we're doing right here is an algorithm called Burrows-Wheeler transform. That's the name of the algorithm here. And this algorithm increases the number of opportunities that we have to do this. If you look at Mississippi River here, it has a lot of I's, but they're all separate. But the code of the encoded version of the Burrows-Wheeler transform, or the transform version, is that very last string here. And this has 3 I's in a row, so it is already better. So I'm writing the untransforming, the decompressing version of it right now. So what we're doing is we're going to zip with. Let me check the actual algorithm, not make any mistake. So add 1, add 2. We always add the last column first. Yeah, okay. So zip with W WST. So that's the first thing we do. We sort this. And let's move this N here. And we call the code loop with the same W, N minus 1, and this. Okay, so now I need to define extract. Extract of W equals. What we want is data.list. I think there's a find searching with a predicate. So it's just find. Okay. So we're going to find the word, which is such that the last one is EOS. So that last of W is EOS. Let's not call it W then. That's an ST. And when we've did that, we do from just because we know it exists. That's risky. And what are we doing? we need to remove the EOS again. So what we're going to do is map maybe. Does that exist? Yeah. Oops. And we do an EOS. We're going to define that function. We're going to capitalize this. Oh. Okay, so I need to write an EOS now. My keyboard is not responding. Okay, here am I again. Things are not well aligned, I think. Okay, an EOS of simp b equals just b, an EOS of EOS, I don't need the parentheses, equals nothing. So we're just telling, don't put anything where there's an EOS. Okay, so decode is now the code loop, capital L of W. Hang around for a second, Coco Pickle, and we're going to show that in effect. That's length of W, and the last in the state is map const. So we replace all the letters in W by the empty word. It's a bit of a trick because no, it's W here. So W is a word, ST is a list of words. It has the same number of words that there are letters in W, I think. So now we're going to define our second algorithm. So I'm going to copy algo 1. And we're going to call it algo, algo 2. And we're just going to do a BWT, and we're going to display the intermediate form after BWT. Okay. Yeah, because that's not an A here, that's a with EOS of A. Now I need some ord A, it's fine. Oh, it doesn't have show. Okay, I'm going to define an instance of show. Instance show A. Can't find my equal. Okay, I guess I'm a bit stressed out. Okay, show of simp x equals show x, and show of EOS equals, I'm just going to print it as like a hat. Okay, so now we're good, and we are going to run algo 2. Hopefully I'm not going to crash on cycles. Okay, didn't work. Oh yeah, I need to run round trip. It's all stop. Okay. Okay. Round trip. Okay. So the Buller-Wheeler transform made it so that all our things are now, look at this. It's exactly what we wanted. The intermediate form is a bit bigger because of the one extra bit, though it's a bit artificial. But it has all of these things. 0, 1, 2, 3, 4, 5, 6, 7, 8, 0. They're now 9, 9, 9, 9, 9, 0, 0, 0, 0, 1, 1, 1, 1, etc. And now we compress to something of size 84. This is more than 3 times smaller, according to my approximate size counter. And it says, oh, there's 9 nines. Oh, there's a 9 missing. Where's the last line? That's interesting. There's a 9 at the end, look. So it's not perfect, but it says, oh, there's 9 9, and then 10 zeros, and 10 ones, and 10 twos, and 10 threes, and 10 fours, and 10 fives, and 10 6, and 10 7, 10 8, and then just the 1 9. Okay. So that's all well and good. We're done, I guess. But no, we're going to make another example. I'm going to call it roller coaster. And it's also lists of digits from 0 to 9. And the roller coaster, it is take 100 again. Otherwise, that's never going to finish. Of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Followed by 8, 7, 6, 5, 4, 3, 2, 1. Okay. So we're going to just look at it first. So roller coaster. Yeah, that's all. Oh, what? Oh, I forgot one of these. And of course, I didn't write the right definition, so that's not going to work. But yeah, that's not the right one. I need to add cycle here. No. Okay, so it gives me 0, 1, 2, 3, 4, 5, 6, 7, 9, 0. Okay. And now we're going to try to do the same as with cycles, but with roller coaster, which I haven't tried, but I predict will not be very good. Well, it's better, I guess, but it is not like excellent because there's 2 different possibilities before 1. It's not really a very good example of what I wanted to illustrate. So here we see that 1s can be preceded either by a 0 or by a 2. So the 1s are split in 2 places. So it's a bit bigger. It's like almost twice bigger as the other one. We can make another example that will be better, and we'll call it Mississippis. Because 1 Mississippi, 2 Mississippi. Except that char isn't sizable. Okay. We are going to say that. Okay. Size. I didn't make char finite. Well, never mind. I can't do Mississippi's, but. So how can we do this? Something a bit more messy than that would be more interesting. Let me think. That's what you get for not preparing in advance. But then again, that's the fun of these streams. So let's roll with this. What can we do? We're going to do a Mississippi lookalike. So we're going to say that. So that's again something of size 100. And we're going to say that m is 0, I is 1, s is 2. So 2, 1, 2, 2, 1, 3 for p, and 1 for I again. Okay. So now I have something slightly more irregular again than the roller coaster. CPs. So again. Okay. And if we put it through the our new algorithm, which is still a good algorithm. Oh well, it's the same size again. Well, but that's because it's the wrong one, of course. That would have been surprising. Okay. Oh, it actually compresses very well. It compresses very well. Oh, I need more irregularity. So let's add a space. That's 4. A river, 5. That's 1. That's 6. That's 7. And that's 5 again. Oops. So now I have something a bit more irregular still. Still compresses. But what I want to say here is that we can see that some things are not quite repeated, but are close. Like there's the 0 here and the 0 here, the 2 here and the 2 here. We can kind of see it in the in one of these examples as well. I should have just pulled that out. So here we have 6 mixed pixies sift. Well, anyway, so we can see there's IX, 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 IX here, and so these are not quite repetitions because we just do repetition of a single symbol. Otherwise, it's a bit complicated to go there. But they are close. So the I here is close to the I here, and the I here is close to the I here. And we said at the beginning of the stream that we can later exploit the fact that numbers with high frequencies are also can be represented with fewer bits, so they can take less room individually. So the next idea is to say, oh, is there a way to make it so that symbols that are close, being close mean being the same symbol, so that closedness becomes frequency. And a technique for that is called move to top. And the idea is that we're going to say that we're going to change the characters to represent numbers which are sorry. We're going to represent to represent the character by saying, oh, it's the number of times since it last occurred, and in a random order at the beginning. So ix, ix, we kind of read like 0, 1, 1 or 0, maybe 0 or some number here, but then x, another number, and that would be 1, 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 and that would be 0. So naturally we have a bunch of 1s because numbers are like close to one another. So that's what we're going to do next. We're going to improve on all of these, on some of these, I guess, by doing the move to top thing. Move to top. So move to top will go to integers, I guess, which is going to be a problem. But for the time being, we're going to say an array, and we're going to say a list of integers. And so move to top is yet another of these ISO. So we use encode, decode, where encode equals, oops, and decode equals something. Oh, the space would be nice. Okay. And basically, the main thing here is that we're going to use a function that moves something to the top. So it takes an A and an AS. It will do A colon filter, only filter different from A A's. So it will take A in AS in A's and it will move it to the front. Is it move to top or move to front actually? Let's have a look. Quick look at bzip2. It's not exactly the same algorithm we're doing. By the way, this is the one before last algorithm, and then we're recapitulating everything. Oh, Wikipedia is having troubles tonight. So, well, whether it's move to top or move to front, it means the same to me. So if I use the wrong one, just substitute top for front when you talk to other people that don't use the same vocabulary terminology. So what are we going to do? We're going to do a simple forum, I guess. So we have AS, and we're going to say forum. We're going to do a run state. What is the variant of run state that we need? No, not that one. Yeah, maybe that one. I will need to import some things, or to run state, eval state. That's eval state, okay. So that's eval state. The initial value is elements at A and $. And we're going to do a for m. It's going to yell at us, but for m. So for each character in AS, we are going to need the index. Can we index these? Sublist, binding list, searching by equality. I want the index of it. Indexing lists. lem index. Okay. So what I want is I will want to output, that's return, from just of lm in list, lm index of, oh, I forgot something. Need to name this value. So we're going to name it lambda a. So, okay, it's a value of type A. We're going to replace it by its value in the list. Well, actually, that's what we need to name it. So, what we're going to do, we're going to do something. We're going to say, we're going to name out equals paste, and so we're going to return out. And in the middle, we need a list as well. So we're going to do stack, and the stack we're going to get it from the state. So that at first it will be the list of elements of A, and we are doing stack here. Okay, and when that is done, well, actually I don't. Okay, since I got, oh dear. So actually, I'm going to undo what I did. I don't need to name it because I named the stack, so that's good enough. Okay. And here, what I need to do is to say, I'm going to put, so I'm going to change the value of the stack with move up a stack. And now it's not happy because A is not in scope. Oh. Okay. That's supposed to be I as a prime. And now I need eval state. So what I'm looking for really is control.monad state. Does that exist? Yeah, it exists. So it's in base. No, it's in the NTL. There's really no way around importing the MTL, is there? I guess there isn't. Well, let's have a look though. Oops. Import control.monad dot st. Definitely not. Dot state. And so I need to, oh, hidden package MTL. Yeah, Ray, have a good night. Have a good trip tomorrow. And well, if you want to catch the rest of the stream, it will be highlighted. Okay, so I need to go to my Caval file and add the MTL. Code to MTL. And I probably need to restart Dante. No, it didn't. It wasn't sufficient. I can revert buffer. And reopen Dante. Okay. Okay. It says couldn't match A with state. Oh, so eval state doesn't have the type, I think. I guess. So if I was in control monad state lazy. Oh, right. So let's just flip it. List event with unit. I don't know why he's saying that. Okay. I'm not sure. I'm not sure. I'll fix that later. So in the other direction, I have a bunch of integers. and we say flip, it will state. So we're going to do really the reverse. Elements add a. And well, we're going to well, mostly it's the same thing. So we except we don't have an a yet. So we need to find the a. So let a equals, and that would be our index. So that's bang bang. Yeah. Oh, I pressed the button in the wrong window. Stack. No, sorry. Yeah, stack. At. So here is eyes. That's my index, and here is I. So we're going to say A as is stack at thing. We're going to move A up, and we're just going to return A. Okay, so alignment's good. So what went wrong? Is val state the right type? So it's state as A and return an A. And that is supposed to be a list of elements, list of integers. Where does unit come from? This is more surprising. So list of A to list of int. Okay. Couldn't match the expect type of int without tool type unit. Okay. I'm a bit puzzled. Why is this? Element index returns a maybe int. Oh, okay. I used the wrong version for him. So finite. Okay. Wow. Here we go. I'm just going to put the type on decode as well. It's and we're going to do algo 3. So we're going to do algo 3. Instead of with EOS, we got integers here. And we're going to, can't read anymore. We're going to copy the Burrow Willis transform. We're going to do move to top, display, move to top. Oh yeah, it's supposed to be algo 3. Okay, what's wrong? Oh yeah, because we're still doing the run length encoding. So it's into int. Yeah, it needs to be finite. Okay. We can, since finite has ord and ec, we can move ourselves, give ourselves a bit of size. Okay, now We can ask for algo 3 of Mississippi's, I guess. A round trip. Algo 3, Mississippi's. Needed next. So what does that look? So now, so the definite size is 92. It's a bit better. But the trick is, I mean, it may be cheating a bit. So I'm not really sure that it gives us a good result because of the integer thing all the time. So blah 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 blah. So here, so all of these have become a lot of zeros. There was 5555. There are a bunch of zeros. There's a 2 here because of the 0, but then another bunch of zeros. So the number of zeros has increased tremendously. And so the runs are not necessarily much longer than the previous one, though you get some of them. You get 0 5 times, 0 5 times, 0 11 times, 0 12 times, and well, yeah, it's about the same as far as length of these have. Okay, they're a bit smaller sometimes, a bit bigger other times. But now all the numbers are pretty small. There are very few big numbers. So look at this. It's 0, 0, 2, 0, 0, 4, 0. So almost no big number. Almost everything is 0, 1, and 2s. And that means that we can use very small number of bits to encode 0, 1s, and 2s, and that will be extremely efficient. So it's pretty nice. Except that, well, there's a bit of a problem with this. So I'm going to rename this move to top 0. Because it's slightly problematic, and let's move to top 0. So I want to make a finite version of it. So I'm going to define move to top, which says type finite a. So for all n a, because I will want to give a value for n, and I'm going to do fin n. And the way I'm doing this, move top. The way I'm doing this is by just adding in a new version, a new ISO after. So we're going to do move to top 0, and we're going to do fin mcfin at n. Do I have the other direction? I'm going to make it and fin takes a fin n, returns an int, and fin equals and fills a fin n I equals I. So mcfin n and fin at n. That is true. So map and map. You could probably do that with a single query, but right. So just add this. So we'll have to provide a number to move to top. for the number of characters. So we have to be a bit careful. So now we're going to do our algo 3 prime. It's really the same one. But instead of this, it's going to be fin n here, or some value that we have to specify ourselves. And I'm guessing it needs to be finite. Here we go. Those are the first characters, very useful. So for instance, we can do this again. And we need 11 characters because it's 9 plus the algo 3 prime. Oops. No. Or at 11. Oh yeah, it doesn't work here. Oh, that's a problem. I could use a proxy, but this is annoying. I can I guess I can do colon set. It's a bit silly, but does that work? Some flag has not been recognized. No, it doesn't manage. Okay, so let's open GHCI. Stack GHCI. And try this. Oh yeah. Round trip. Algo 3 prime. 11. Mississippi's. Right. Set. -6 type applications. Okay. Okay, well, it's not very readable, but it's supposed to be more or less the same as the other one. The numbers are not quite the same because the encoding of integers and of finite numbers is not the same, the size of it. But otherwise, it's the same type. So we can kind of see all these zeros becoming. Something you might notice, and that will be important, is that the only numbers that are repeated are zeros. So here 10 is just the 1, 6 is just the 1, 0 is 5, 2 is just the 1, 0 is, and that's by construction, because if you're a repetition of something, then it's really the previous character, which is always 0. That's the definition of it. So I don't know why that doesn't work, and we'll fix it up by doing more type specification later. But it should do the same thing. Okay. So we're going to exploit this, the fact that that only zeros are repeated, to make a new version of run length encoding. that only repeats zeros. But before we do that, we need to learn how to count. And we need to learn how to count in base 2. So there's 1, and then there's 1 and 0, that's for 2, and then there's 1, 1, that's for 3, and then there's 1, 0, 0, that's for 4, and that's 1, 0, 1 is 5, 1, 1, 0 is 6, and 1, 1, 1 is 7. Okay, this is all good. But the problem is that in this thing, there's plenty of way to write the same numbers. I could just write, so the same line can be written 0, 0, 1, and then I can add 0 here, and then 0, 0, 0, something. There's just, I can write these numbers in plenty of ways differently. But I can do something very, very weird. Is instead of counting with 1s and 0s, we can count with 1s and 2s. So we're still base 2, and if you're used to numeration system, we will have 2 digits like normal, but we don't have a 0. So we can't count 0, but we can count every other number. Look at this. That's 1, 2, and then it's supposed to be 3. So that's, what is 3? Let's have a look. It should be a 1 there and a 1 there. Yeah, of course it is. It's the same as before. But now we need to do 4. And 4 is a 1 there and a 2 there. So that's 2 for the first digit, and then 2 for the second digit. Well, that's 4, indeed. And then 2, 1. That's what that will be. That should be 5. No, it isn't. Yes, it is. Yes, that's 2 times 2 is 4, and 1 is 5. That is good. And 2 and 2 is, of course, 1 more. And then, so that's that would be 6. So 4 plus 2, 6. Now, we're going to do 7, which is the last number of the previous one. And that's, of course, 1, 1, 1 again. And then 1, 1, 2, and 1, 2, 1, etc., etc. And this, I can't add zeros because I don't have any zeros. So every digit is significant. So we're going to code non-zero sequences of zeros with these things. So I need to introduce a new type again. So data with runs, and so it's either an integer. It's always an integer. So we're going to call I. I'm a bit lazy. Of an integer, and otherwise it can be 1 or it can be 2, and these are the lengths of a run. So we're going to encode runs that way. Remember, all the runs are runs of zeros. We know that, so we can completely ignore the rest. So this is also finite, show, etc. So we can first we can derive or eke and ord, and we can instance. Oh no, it's not an int. I'm sorry. N.net, and that's a fin n. That's really important because I want it to be finite. So instance known nat n with runs finite with runs n. So now we don't have any integers anymore. That's the entire point. And so elements are map I to elements of fin n. So all the elements of fin n, and then we just add at the end 1 and 2. Deriving. Okay. Just in case, let's put GHCID again. mean, Dan should be enough, but GICD ID is more flashy. So it's also sizable. Now we know exactly how many elements we have, so we can just do. We can just use log. So that would be a bit more accurate. And we expect to have a lot of ones and twos as well, especially, and so we expect to see them having small code at the end for really. Where the size of, so we're going to ignore the element, and we're going to return log base 2 of log base 2. Because I think I made myself. Oh yeah, I just have a. Okay, I can derive it. Okay. Okay, so what I'm going to do is I can remove this and say, okay, because it's finite, we can just, so that's not fin n, that's with runs n. What did I write? And that is not fin, that's with runs. Okay, deriving, no, not deriving, instance show, so we want to print all runs with run of n where show of I equals show 1 equals R1, let's say, and 2 is called R2. Now we want to encode a number which we assume bigger or greater than 1 into a list of these. So int to run takes an integer, returns a run. Returns no with run of n for any n. So int to run so how can we do that? N equal let's have a look at package and look at the mod operator. It's mod 2, yeah. I'll just do something like that. Let n2 equals n mod 2. Where are you? Okay. Okay. In if n2 equals 0, then so we're going to divide by 2. Is there a quote rem? There's a div mod. Okay, we can do that. So we can use view patterns because that's. So we're going to do div mod to oh no, that doesn't work. Okay. Okay, so we're going to divide by 2. And we're going to do that's half n and 0. Okay, that's a bit ugly, but and if we have this, the value is 2 colon. We're writing left to right, so the numbers are the digits are written. So the instead of like here 1 2 would be written 2 1. That's the general idea. So that would be int to run n2 minus 1. So we remove 2 and divide by 2, which is the same as dividing by 2 then removing 1. View patterns. Oh, it doesn't manage to apply view patterns. Okay. With runs. Oh yeah, it's a list of these. Okay. And so otherwise it's 1. We're going to do 1. And we don't remove to this one, so that's just n2 here. So for instance, int to run of 6 should be 2 2. Oh, that's not a very good example. 5 should be 1 2. I think I just broke my into run. So I think oops, that's not what I wanted to do. I think the general idea is that it's div first and mod second. So that should be, can I? Yeah, okay. But this one will not work, no. So this one, I will do this. So it seemed to work very well. So let's, oh yeah, we never stop. That's bad. Right, forgot one of these. Int to run of, say, 0 equals, yeah. Now, still doesn't work. Okay. Oops. int2 run 0. That works. 1. That's not correct. 2. This is hilarious. Oh yeah, that's because they were correct before. Okay. Now, on R. Yeah, that's better. 3. What am I doing? 4. That looks correct. 5. Okay. Can I start over? No, I think my can I kill process? I don't know. There's somewhere something that is doing computation, but I don't know which one it is. Maybe I can kill this. Okay. Okay. It's looking pretty bad. I can open yet another Emacs. I guess I will do this. Okay. Light theme. Oops. Source lib. It has a very imaginative name. Now I can turn on Dante. What's wrong with it? Oops. Yeah, I don't know what's wrong with it. Evidently, I have no idea. I don't know what I'm doing. Okay, whatever. So we know how to turn an integer to runs. So now we're going to do our run length encoding revisited. So we're going to call it 2. And it's going to be specialized to fin n. And it will return a list of fin n, of course. Okay. And it will return a list with runs of n. So the idea is that it knows that only 0 can be a run. That's really important to equal. So we're going to use run length encoding. And we're going to follow it by ISO pack unpack. Well, we unpack pack. Where unpack will basically be calling into run everywhere. if rather 0 and just remove the rest, and oops equals underscore oops, and pack we'll be calling the reverse. We should probably do that. Let me encode this. Okay, so int run to int. Right. Int run to int of 1. It's a list of these. Sorry. Equals 1 plus 2 times run to int wow, sorry, and ours. So ours and minus 2. Oops, we do 2 here, and with something else we fail. It's not the most elegant. But we're going to make it work. Oops. I'm doing that mispress a lot. Okay. So now, what we're saying is we have a bunch of infinite together with their integer, with their length. But we know that. So if so, we're going to take one of these. So that's the number and its length, the length of its run, and if I is 0, then so it's not map that we really want to do. We want to do concat map. So if I is 0, then we're interested in the length. So we're going to do int to run n. Otherwise, we have the symbol that we want to print, and the symbol that I want to print is I, and so I just do with an I, so I of I. Yeah, no net. Okay, fair. In the other direction, we're going to start with the coded R's, and we're going to group by so we're going to do is digit with runs n to bool, and is digit I, well, 1 is true, is digit 2 is true, and is digit of something else is false. And so here we're going to take two R1, R2, and we're just going to ask them to be both digits. So is digit R1 and is digit R2 of R's. So now The only thing we have to do now is to call pack1, which I haven't defined yet, but it's too big to define a single thing. So now we have a bunch of lists. They're all of size at least 1. So pack of I. So we either have a singleton list with an I, pack1, sorry. So we're going to do something with this. I guess map. Okay. So map of pack I. So that just gives me an I. And if I have pack1 of something else, of ours, then I just do runt. Sorry, it's in1. And here I just do 0 with run to int of ours. This is where we exploit the hypothesis that only 0 only 0 can have a length of more than 1. So now we can redo algo 3 a third time, I guess. But we just got rid of algo 3 second. And instead of run to length encoding, we're going to do run to length encoding too. And instead of fin n int, we have with runs n. Okay. And so we're going to do an algo 3 10 equals algo 3 prime 3 second at 10. Okay. That's just for the ability to print things. So we can remove this, and this will be 10. This will be 11 actually. Oh. 11. And this will be this one, okay, like this. We can remove all of these. Yeah, and it's not algo 3, it's algo 3 underscore 10. No, I don't need this. Oops. Okay. Fantastic. And now we can take we can test this on Mississippi's round trip. I'll go 310 on Mississippi's. And ooh, that's no good. I can't do this. Interesting. So the decoding went wrong. We have to figure out why. So which one couldn't do this? Yeah. Oh, yeah. Okay. Let's try again. Much better. Except that the output is not the input. Oops. Where did that go wrong? Where did we go wrong? That was correct. Okay. So I'm guessing that's my final thing that went wrong. That used to move to top, right? Yeah, it did. Um, 10 ones. Okay. Let's see if that's my decoding that went wrong. Oops. The consequences of live coding. Okay. So from display debug oh yeah, something have changed. That's a bug. There's a bug in move to top, I think. There shouldn't be two ones in a row. But that didn't occur before, did it? Oh, yes, it did. Aha! Ha 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 ha! A bug, I tell you. A bug. Can there be two ones in a row? Oh, yes, actually, there can be two ones in a row. But we can choose not to treat them as a sequence. Yeah, there can be any number in a row. Now I'm confused because you know when you think something is true and then suddenly it's not, and it's obviously not, and you never know why you believe it was. So when I said earlier that only zeros can be a sequence, I was wrong. But only zeros represent a sequence, which is fair enough. So what is the consequence of this? The consequence is that that I'm wrong. So let's look at this. So then it is not this. Okay. We can do repeat n like this. No, it's not repeat, it's replicate. I can replicate n. Where is I repeat? Okay. What? Okay. Now that will work. That will work. Okay. What happens if I do round trip now? Oh, I know what. That looks much better. That's the actual round trip. And now we have our compressed form that uses 171 bits. It seems less good as before. But it's because we ignore the fact that there are very few numbers. So we're going to be able that are frequent. So we're going to be able to do some some encoding of them in a better form, which is really the last thing that we have to do. So I take a bit of a break here to talk about how we're going to do this. So the most typical way to do this is called Huffman coding. And I'm guessing there's a Wikipedia page. But Wikipedia has had troubles tonight, so we might not be able to see it. Right now it's a white page. We'll see if it gets slightly better in a few seconds. But anyway, what is the idea? We want to say, like, there are a ton of R1 and R2, so let's just use 2 bits for these. But on 2 bits, I can only code 4 characters. However, if I say, let's say if it starts with a 0, it's so 0, 1 is R1 and 0, 2 is R2. 0 is 0 is R1 and 0, 0 is R2. Then all the numbers that start with a 1 can be used for something else. And for instance, I can if there are 10 other characters, I will need 4 bits for these, and I can just assign 5 bits to each of them. So suddenly, so 1 plus 4 bits. That's completely legal to do. However, I can remove my debug, by the way. Oops. So Huffman coding does that by just you count everything, you count the frequency, and then you assign a number of bit that is sort of okay. And then you have a sequence of bits. But I'm going to use something that is a bit more entertaining and slightly more complex at first sight. It has a good advantage over Huffman coding, which is Huffman coding. Sorry, which is that I don't need to have a way to store a dictionary. So it's just actually the code of this will just be one number between 0 and 1. So let me show you how this works. It's very entertaining. So I'm going to draw a picture. Space. Okay. So let's say this represents the interval from 0 to 1. So what we're doing is called arithmetic coding. It's different, and we're going to steal some implementation here or there, but it's all fairly simple. So here, Huffman generates a tree like this, and the tree lets you decide what number of bits to use for each of these. It says, there's I don't know. So in that case, the most frequent character is a space, and it's here, so it will have 111 in this particular example because it's not too unbalanced. but other things might have a code that is bigger. But of course, it can't really start with a 1 if it's bigger. Well, it can, I guess. But they have a discriminating sequence to be sure that you can recognize what you're reading. Anyway, you also need to pass a dictionary saying, oh, that this particular sequence is a space and this particular sequence is a 2. But we're not going to do this. So imagine we have 3 characters and we have discovered 2, 3, 3, 3, 10. That one character, is used 50% of the time, call it A, and one character is used 25% of the time, call it B, and one character is going to use is also used 25% of the time and call it C. Okay. So what are we going to do? We're going to say that all the numbers here code for a number that starts with an A, and all the numbers here code for a number that starts with a B, and all the numbers here code for a number that starts with a C. And this interval is twice as big, so you need less data to code a number in it. Just trust me on this. So we get an arbitrary number, and we get an arbitrary number as the code, and we look, oh, which interval is it in? Oh, it's in that one, so it starts with an A. And then we kind of zoom in, and we go into that interval, and okay, so I'll just copy it with my mouse because I'm being clumsy. Okay, and we also divide it in 2. And that doesn't quite fit, but we just have to imagine that there's that we divide it in 2 twice. So, okay, so there's no good way to do this. I should double the size of these. So, yeah, it doesn't quite fit, but it's supposed to be the same interval, and we divide it the same way. So half for 1, a quarter for 1, a quarter for 1. And then if we are in there, that's a number that starts with AA, and here is a number that starts with AB, and here's a number that starts with AC, etc. It turns out to be very, very effective. But of course, we're going to start with an interval that gives the same intervals for everybody. And then we're going to evolve them. So maybe we should do that first, see how we can take into account the proportion of things. So we're going to define a model. The model is what gives us all values. So a model is a map. In our case, it's from anything. So it's a model for symbols. For symbols, and it's a map from S to int, which is the count of that symbol. And I haven't implemented. So I've got to import data.map and import qualified data.map as map. And that will not work because I need to open containers. Here. Okay, refer buffer. Okay. So we're just going to count things. So whenever we're going to do update model, which takes a model of S, a new S, and returns a new model of S. And an update model will be we'll just like, we need S to be odd, of course. Update model. I'll take my model and my symbol and say, so I never remember the good functions. There's a modify function somewhere. Imagine how much more efficient I would be if I remembered the easy functions. Is that insert with? Not even. Adjust. Yeah. The map.adjust +1 and an S and M. Okay. Actually, we're going to also create our initial model, which is important, and it will be a perfectly balanced model. So it's going to need a finite S. That's where the finiteness hypothesis come into play, really. That's the most important part. And returns a model S. A new model. Equals map.fromList. And we do map of fun. Not fun, that's not a camel. S, so a symbol to S1, and we do that on all of the elements at S. So I need to write for all S. Okay. Okay, so that's the general idea. We have a model. We always assume that there's at least one use. That's for so that everything makes more sense. And then we are going to transform this into a list of boundaries. So boundaries. So it's the way to transform the model in a list of intervals, basically. So we're going to take a model, odd S, model of S, and it will return a sequence of rational. I don't know what is happening. Okay, I think I know what's happening. What's happening is that I'm pressing random buttons. Also, the last line was missing. Okay. Take an M. So first, we need to know total equals the sum of there's an element function here in maps, I guess. Come on. There's a traversal. I guess it's traversable, right? Maps are traversable. or foldable at least. Foldable traversable. So if I just do sum of m, and I've got the total. Right. Well, that's easy. Now, what do I want? It's not really a list of rational that I kind of want. It's a list of, I guess, symbol rational. It could be a map of symbol rational as well. But yeah, list is fine because I'm going to look at them in order. Yeah, if it was a list, it would need to be intervals. If it was a map, so let's start with this. So so how do we compute that efficiently? Well, not efficiently, but effectively. So we want to know the current. So the proportion. So we can divide everything by the total, but then we need to take the sum of the preceding values. Which sounds easier in my head. Rational. So partial sums are usually taken using scanl. That should work, but I need to unzip and then rezip, I guess. To list. To ascendant list would be better. So map to ascendant list m. Sure. Okay, so we have an ascendant list. We're going to give it a name. Actually, we're going to unzip it and give it a name. Let sims quantities okay, equals unzip in then we say scanl plus 0. It's probably not the right order on map fun q2 from integral q divided by total. Pattern syntax. Oh no, that's just me being an Ocamelian again. Ocameler. The type is not right indeed, because we want let b's equal. I guess we can just do this. it's 2, and B's equal, this shouldn't be these, but we want the tail of this, because if I remember correctly, I'm going to check right now. Scanl returns a 0 first. In that particular case, I don't really care much about the 0, I think. And it's one more element. So I just drop the 0. The elements are in the right order too. It's quite amazing. I drop the 0, and then I can zip again. Sims with B's. Dante doesn't see an error, but there apparently is one. Couldn't match expected type A. 472, where is this? Do I need to put parentheses around these? No. Oh, but I need to put Q's here. Zip is applied to too few arguments. Yes. It shouldn't. What? It really shouldn't be applied to a single one. Actual type int. Really? Oh yeah. Okay. Now we have rationals. Fantastic. I'm going to steal some code from I'm looking for something. We're going to open a blog post from Jeremy Gibbon, because there's plenty of useful code there that I can just like steal. Here it is. So there's a code about arithmetic coding, a blog post about arithmetic coding. I'm going to put the link here in the code. So if you're following that from the recording, you see an advertisement. I'm so sorry about this. Okay. If you see a there's in the recording, you can fetch the link from the GitHub repository. So now we can do like something like data interval equals interval rational. Yeah. And I'm not. So what's really interesting. Okay, so Yeah, it contains is a useful one. So contains. I'm gonna use the thing in the different order there. Rational. No, actually, that's right. Interval. Rational to bool contains of interval LR x equals L smaller or equal than x, and x is, yeah, there the intervals are open on the right and closed on the left in that particular algorithm. I don't know that I need includes, so I'm not going to do it right now. Narrow and wide, and narrow is the most important. The narrow is the operation where it's take an interval and squish it into another interval. Interval, oops. Space, interval to interval to. I can't just copy paste the code because of how it's rendered. I think they're all images. Should I make that a bit bigger? I guess. Oops. There are advertisements everywhere. I'll try to keep them off screen. Narrow, that's an interval. That interval, PQ in that case, and that is interval of weight IP, weight IQ, and weight. So this is just boilerplate to do some interval arithmetic like interval, rational, weight, interval, LR, x equals L plus. So rational are exact arithmetic, so we don't have to worry about overflowing or something like this. They are arbitrary size. In exchange, they're not very fast, but again, we don't care all that much. Okay, and we have widen, which is just as important. Widen, that's the opposite operation that we'll need to do all the time. Interval in interval. And widen. So that's, oh, sorry. That's I interval PQ equals interval. I don't even know that I need this, but scale IP, scale IQ, and scale interval to rational to rational. It's going quite a bit faster with the interval LR x equals x minus L divided by R minus L. Yeah, that's just me not respecting my conventions. Okay. Now we can do oh yeah. We can define encode sim and decode sim, but let's do them inside our thingy. So what we really want to do is define. So define arithmetic encode to be an ISO from some list of symbol to I did a special type called decimal. I think it's just decimal, and it's ISO encode decode, where encode equals, I should have made myself a macro. That's the one. Decode equals here. ISO prime. I think Dante has just given up. Dante's broken. We might try it again later. So we need an encode sim. So let's do for all s. We need encode sim to just do one symbol at a time. It takes a model and an s and returns an interval. And so how do we do this? Okay. So to do this, we can make a map of intervals. So we can do oh my god. Oh yeah. No. We can do intervals. Take odd s. Model s2. Yeah, my typing is becoming weirder and weirder. No, model. No, it's not model. It's map. No, sorry. Model s to map of s and interval. And intervals equals. So we could do let b's equals boundaries. Shifted equals 0 colon map second boundaries in, and we can do zip width. So as we need an s and right followed by a left, and we can do pair s and interval lr, and all this we can do a map dot from list. So I don't remember what I did that, but oh yeah. So that encode sim is simply it's simply very slow, but it doesn't matter. S equals what's the name of the find function? Singles in, from set, from list, insert, adjust, update, alter, lookup. Lambda lookup. So we are looking for S, and we are looking for it in intervals of M, I guess. Couldn't match expected type 80, 81 with model has 0. Where? Okay. Yeah. That's because it's supposed to be B's here, and here is boundaries of M. Okay. S interval with A2 rational. Zip width applied to too few arguments. Uncanny. Couldn't match expected type. That was. Oh yeah. Still uncanny. 512. Model of S. Yeah. Okay. And decode sim, I guess, is decode sim takes a model as well, but takes a rational. And returns a symbol. And decode sim takes an M and a rational X. And to do this, we're going to use interval boundaries this time. And what are we going to do? So we need lists, and we need to find the first element of this that verifies a predicate. So that was find, right? In searching with predicate find, the leftmost element with the structure that does what we want. So we're going to do find, and we'll have lambda s. Well, we don't really, we can ignore this, but it has a boundary B here, and we say the first so that the boundary is bigger than X. Strictly. Then when that is done, we return, oops, I'll manage. So we return first of from just of this. No? Oh yeah, that's because symbol is S. And again, it's oops. What am I doing? I don't know why I don't manage to press the, well, anyway, let's jump there. Okay. Yes. Okay. That is not where I was looking, what I wanted to look. So encoding is, I think, can we get away with a 4? I think we can do a 4. It's not here. Right. It doesn't matter much. So what do we want to do? What we want to do is repeatedly apply encode sim and use the new interval, and so our state is a model as an interval. Initially, it's the new model and the interval 0, 1. And which we're going to give a name to, by the way. So unit interval, unit interval equals interval of 0 and 1. And how very Spanish of me. And so we're going to do that for every element of the stream, and at the end we get a model and a rational, and we do an interval, and we do something with the interval. So encode loop. Well, encode 1. Let's just say code 1 is a state of model S interval return. The return time of this is unit, I guess. Yeah, because I couldn't completely ignore this. So it takes an S, sorry. So encode 1 equals of S equals so let EI equals encode. Sorry, we need a do. We need M and I0, which is the ambient interval, with get. Then we encode the thingy. We encode sim ms, and then the real interval. So we put, and we're going to put something. So we can put update model ms and narrow I0i. I'm pretty sure. That's going to be annoying to debug. Now I need state again. Oops. Control monad state. Yeah, that one. That one. And there was eval state, and there's exec state, which is the one I'm interested in. Okay. So encode many takes a list of states, a list of token, and returns a an interval, I guess. Especially it doesn't return the model. I don't need to return the model. That's the key part. So we're just going to, at first we're going to be pretty imprecise in our coding, but as the stream progresses, we're going to have fairly small things. So uncode many, it starts with of s's, well, yeah, more of s's equals. So it will be a first of exec of flip exec state. At first we have new model is the name I gave it. New model and the unit interval applied to, and we can do for m. This time that works. For m ss and encode s's and encode 1. Yeah. And finally, encode. So encode will do take some s's as well, and it will do let so let interval lr equals encode many s's in I think oops. I'll manage. Find decimal between. So hi. Find decimal between li, which is a function that I pre-prepared. This just picks a number that writes in decimal notation between these two numbers, between L and I, which are. It's just for more elegance. It can be any rational number, but right now it will be a number written in decimal notation with digits from 0 to 9 again. So 515 is decode, yeah. So to decode, do I actually need widen, or is it just? Yeah, I guess I need widen for some reason. I don't know why yet. So anyway, let's try to make decode work. So decode is a bit different, I guess, because we're generating. How do we do decode? So I'll use oh, I need an end of stream character again, I suppose. Okay. So we'll changing something in a second. But decode 1, we're going to use an unfold thing. So we're going to be much closer to the code here. Take a model of S and a rational, and returns maybe symbol. So maybe parenthesis symbol model rational. Decode 1 equals just always. So that's the code sim of, I kind of need the M and the M and X here. So MX, that normal. So that's the first symbol. So I say, my rational is in, so my rational is in there, for instance. So I'm going to look up in here. So I would have changed something, but then instead of looking in here, we're going to just blow this up until it's size 1. So we're going to multiply the rational as well. That's the conceit of that particular implementation. I get it now. Okay, so then you we're going to change a few things in a second. So just this comma, we need to update the model. So that's update model M. Oh, I need S. Okay. Let X S equals in. That's S. MS, and finally scale code sim ms and again symbol is S, model S. Copy pasting is fast, but it's not intimately fast because of because of all these mistakes. The code inf t takes a rational and returns an infinite list of S. And the code inf t of X equals unfold I of a decode 1 and new model and X. So now we need to change something because I need to add in a type. So really, we're going to do a with EOS here. What we're going to do here, we're going to add to add EOS. I'll probably define that function somewhere. Equals to a list of symbols, and that's map sim xs plus plus EOS. Also, rem EOS x's, and this one can be infinite, but we have a take until, I think. Take until. No. We have variants of take. Maybe take while. Okay. Right. So this is not very big, but well, anyway. So we can take while. It's not going to be quite sufficient. So not EOS. Not EOS on X's. And now we're going to just remove sim in front of it. So we're going to map backward sim S and S. Okay. Here we're going to say that we are going to say that no, we have a decimal X. We're going to do rem EOS. Oh, EOS. I forgot to do add EOS here. Rem EOS applied to decode many of what is it now? What we want to do is 2 rational of X, which doesn't exist. Decode infinity, sorry, infinity. Oh, 2 rational already exist. Dec 2 rat. Let's call it that way. Yeah. Oh, let's do that below. Dec 2 rat takes a decimal, returns a rational. Dec 2 rat of decimal integer int equals from integral. No, how did I write it before? X and n. x divided by 10 to the power of from integral, oh yeah, well, n. Okay. So I'm going to try and revert the buffer. See if Dante manages to restart. Dante error. Oh. Okay. So now, right, because this should be with EOS, and we're going to paste it pretty much everywhere. Oops. This one, and this one, and this one. Unit interval. Oh, I lost Dante again. 520. There's a typo. Oh, that's the typo is here really. Nope. What? Okay. No. Okay, well. Okay, did I manage to write it correctly? This is a bit much for Dante, apparently. Right. It should be really for all S. So I could just abstract over this. But it's just as easy to do everything on assuming there's a with EOS. Doesn't make much of a difference. Where is in folder? Let's try to do that again. Event buffer. No, sorry. Save, okay. Dante mode. So second, I guess. Map lookup. Another one. Here. Yeah. What? Oh. Here we are. And we're good. So we can now do the last thing, define all latest algorithm. Copy this. Our latest algorithm that we will call algorithm number 4 does exactly what we've done so far. But at the end of this, we'll do at the end of this, and there will be a type problem, but okay, do arithmetic encoding. So it's called arithmetic encoding, and then display arithmetic encoded. Okay. Yeah. And so the type of this is just a single decimal number. All of this disappears, so I'm going to have type issues. Encode, it's arithmetic encode. Okay. So we're going to force it to be fin10 here for simplicity. It doesn't really strictly need to. And move to top will be at 11. Sorry, move to top. What's the type of move to top? Yeah, at 11. Okay. And now, if everything went well, we can do a round trip. Of algo 4 and of Mississippi's. And with a bit of luck, it's not okay. Round trip in what? Round trip is not in scope. Oh yeah, that's just, is that just because everything is broken? Okay, so you know what I'm going to do? I'm going to go to GHCI, stack GHCI. I'm going to see it here. Even if the font is a bit big, I don't think I can. Yeah, I can't really change it. Oh yeah, I can actually. Fantastic. So it's going to be a bit better. And we're going to do round trip of algo 4 of Mississippi's. Mississippi's. Okay, so I don't want to be smaller than this. So we start with our input, which basically spells Mississippi rivers many times, like this. 0 is M. And we do the Burrows-Wheeler transform, and we get a lot of lengthy things that are the same. And then we move to top to Burrows-Wheeler seems to be encoding so increasing the size because of the additional hat thing, but the end of the end of stream symbol. But whatever, it's just mostly the same size as this one. It's got like an extra couple of bits. Then we move to top so that there's zeros everywhere, and everywhere that starts a 0, it's almost always a 1 and then a 2. And non-1 and 2s are very, very rare because of how BWT, Burrows-Willows transform, has sort of makes things similar close by exploiting patterns. Then, shouldn't be compressed here. It should, here it should say, we've just done the run length encoding. So we've replaced every sequence of 0 by a coding in terms of R1 and R2 of the length of the number. And again, R1 and R2 are 1 and 2, digits 1 and 2 in binary, which is which has a canonical representation for each number different than 0. It's quite exciting. So we see a 1 and a 1 here, so that could have been made shorter, but it is rare enough so that we don't have to care that much. Then this is encoded as, well, it's pretty disappointing. So it's encoding as this one number. It's pretty big, and it requires 157 bits to decode. 12212213145. That looks correct. The decoding looks correct. So we divided the size by 2, basically, and this is the entire representation of Mississippi rivers 100 times. So I don't know how many characters that is. We can. Does that work? No. So I can't really count it, but that's what it is. And if we run our things on something a bit a bit more compressible, then I still get a pretty big number. So that was cycles. Yeah, cycles. I get something of time 133, which is still the smallest we get so far. And of course, nines will get a fairly small number. It's not very small though. So the beginning of the number is just the encoding of the size. So the number wouldn't augment that much if we take bigger things. Like if we cycle, I'm just going to try this just once on something of size 1000, understanding that the algorithms are very much quadratic, and 1000 starts to be a bit, and so we could do Mississippi's 1000 equal take 1000 of cycle Mississippi's. This is going to be a bit weird. Okay, and so we go and we do a round trip of Mississippi's 1000. Let's see how it goes. It is actually pretty fast. The decoding isn't. So the number is about twice as big. So 243 characters, but the initial stream was 3,000 bits, and we compress it to 10%. That's quite amazing. The problem is that apparently our decoding algorithm is slower than slow and doesn't seem to finish in a reasonable time. So there you have it. This is how to make a compression algorithm. Oh, we've done. We're back to the initial size. Well, it's okay. 1000 is doable. Anyway, this is a general idea. bzip2 is a bit different. For instance, it uses Huffman coding, that kind, for the final entropy coding. That's the thing where you try to optimize for frequencies of digits. And it has a few different passes, but the general idea is this. This is bzip2. It's one good algorithm if you want to optimize for storage. So what did we do? What's the algorithm at the end of the day? The algorithms say we start by making more repetitions and by making similar things close. That's the Burrows-Willis transform. And then we are going to transform close identical things into small numbers, so that x ix is 1111, and but ab is also 1111. So that makes the same, because everything that is similar is more or less close after the previous transform. It makes a string of very small numbers. When that was done, we encoded any sequence of zeros using twos and ones. So transforming a sequence of zeros into a logarithmically smaller quantity. And finally, we use frequency using arithmetic coding to get a number. It's a decimal number. Usually you would take a binary number because it's more precise. And we get on. So the arithmetic encoding is not very good at first because it doesn't know about frequencies. But as the code progresses, it becomes extremely efficient. And on the repetition of Mississippi rivers for 1,000 characters, we obtain a compression factor of more than 90%. A lot of it, like 90% is obtained apparently by just the run length encoding, because there's so many zeros. Look at the many zeros that we have. And finally, we get another entire 2/3 reduction factor. So it's reduced by an extra third of its current value by the arithmetic encoding. And so that was the summary of it all. I hope you enjoyed this 3.5 hours we spent together. That involved me fumbling on my keyboard quite a bit. But at the end of the day, I hope this was informative and that you leave this video knowing a bit more how one does arithmetic encoding. One does a compression in general. And and so that, again, actual algorithms from the shelves, like things that run on your computer, use these sorts of principles. Not necessarily exactly that, but mostly it's this sort of idea. Trying to find patterns, trying to exploit patterns, and finally, it's almost always an entropy encoding. Very often the Huffman coding, because it's better known. But arithmetic coding is pretty cool too. That was all for me, and I wish you goodbye.